in this episode of Street Talk Unplugged.
On the other hand, I'm always careful now, like as of recent specifically, with phrasing everything as a search. Because a search kind of entails you have a goal. I'm not sure if that's true in every circumstance nowadays.
A scientist leverages control to gain knowledge. They set up controlled experiments to gain new knowledge. An engineer does the inverse. They leverage knowledge to gain control over the future. And the same with this duality of the exploration versus exploitation trade-off.
Today we have Alexander MATTICK, who is officially the smartest guy on Yannick's Discord. I hope you enjoy the conversation today. If you like content like this, please consider hitting the subscribe button and also rate our podcast on Apple Podcasts. Anyway, enjoy the show.
So I'm currently a master's student at FAU, so Friedrich Alexander University in Germany. From a theoretical point of view, I'm very interested in kind of the idea of having known parts, so fixed elements inside neural networks. Be that things that are just known to work, so like things like known operator training, which we do at FAU, but also things like having known optimizers. So something like having a simplex algorithm in the middle of a neural network, which can find like certain solutions because we know how it handles. On the extreme end, of course, there are then things like logic, where you can say that if you have, for example, you have a neural network and you have a symbolic layer on top of it, which you can very easily handle, you can very easily like explain what it's doing. So basically you have these two stages, maybe multiple ones which are intermixed. We have these statistical methods, which do like lots of the heavy lifting where you don't actually know what the task is. So it's very hard to define what a dog is, even if you like intuitively know it. But on the other hand, once you have done that parsing part, so once you have decided what this is a dog, then you can start doing like symbolic reasoning. This layer is very much under research at the moment.
Okay, so something interesting about everything you just said is none of those are topics that we've reached out to you for a discussion and kind of, let's say, help on in the past. So
I should actually stress we thanked Alex very much for his help on the previous episode with Leantap and Balestriero. And that was all about, in particular, Balestriero's spline theory of neural networks. And I must always stress that we're talking about MLPs. Clearly, some of the other more modern flavors of neural networks presumably do extrapolate in a way that MLPs doesn't. But Alex, would you mind just giving us a little bit of a flavor on that conversation?
I think it's a very interesting idea of how you can model the internals of a neural network. Because we know that neural networks have to extrapolate in some shape or form. We know that, for example, in the validation set, we know it works fine. But we also have to have a model which explains why if we go sometimes even very small amounts outside of the training data, that it suddenly stops working. I think the idea of having basically planes or regions where the model basically kind of does the same thing is kind of a very good explanation for that. That you basically just cut the space rather than having the actual smooth interpolation.
Right. It's an intuition that maybe is a bit subtle or difficult sometimes for even people that are very well versed to understand why, we even think that that's a cool intuition, because we've had multiple people come back and say things like, well, yeah, but if I wasn't using ReLU, I was using a smooth function. It just completely trashes all your argument, right? And no, it doesn't. That was the perspective I was coming from before, is that, hey, if the activation function has a smooth area, in my mind, I was imagining that a neural network was really making use of that smooth part, that it was, stretching it and putting the majority of the data sitting on that curve, because of course, smooth curvature is going to be so important. But the lesson of the spline theory, the lesson of the dominance of ReLU and everything is no, that little curve part is almost irrelevant. All that really matters is it's a toggle that turns off and on these linear, cells.
I think people really underestimate that the reason for neural networks working on the scale that they do is really because they're very general models. They model things in a very simple language, basically like these affine splines, and this is why they generalize. if you then start doing like very specific things, like polynomial regression, for example, is also something you could technically do. But then you get like very much, like very difficult dynamics to handle. It becomes
Right.
basically impossible to kind of go into the future like without having any knowledge about how the polynomial is going to look like.
One of the big ideas in neural networks is that they learn increasingly abstract representations. And just talking about MLPs for a second, what I took from Randall's work is that that's not the case. The neural networks are just slicing and dicing the ambient space. And in a sense, that's not learning increasing abstractions. I think a lot of people, when they think about neural networks, they think about the OpenAI microscope. And that quite clearly shows that if you solve an optimization problem to find an input image that maximally activates a logit or a layer or a neuron, it looks like some of the neurons might be learning an entire face, for example. But forgetting about that for a minute, do you think MLPs in this view are learning those levels of abstraction?
The problem is that in a neural network, you can't really talk about objectness as a thing. So if you want to basically approximate this idea of having objects and higher levels of abstraction, which are also basically higher like groupings of objects, then this might be just the same as saying, like, we have specific features, specific like attributes in the ambient space, and we chop it up into specific regions. So for example, if I have like my headphone case here, if I just say like, this is the same as saying I chop up the space until I have this as an object at the end, which is just basically just an activation part of the network then.
Well, I mean, okay, so maybe that's true. I mean, I don't know. We don't know. But on the other hand, we do have the human brain as kind of an extant example of a neural network that does these certain types of behaviors that we're interested in replicating. And if we look at the adversarial kind of world, the ways in which neural networks are deceived seems, radically different than the way in which human beings are deceived by, say, a magician or something. So, I mean, if you put a little rainbow pixel on a bus, on a school bus, I'm not going to all of a sudden decide that it's a jackhammer, right? So wouldn't that kind of observation, I don't know, doesn't it at least provide some intuition that maybe it's not the same, is that abstraction isn't the same as just chopping up the space in an increasingly finer detail?
I mean, again, that depends on what exactly do you mean with abstraction in that case. Because humans have a very concrete notion of abstraction. They have objects and then groups of objects and then groups of objects that kind of goes up. So I could, for example, say, okay, this is a car or this is a BMW. And it's kind of the same thing. It's the same general idea. In a neural network, you don't really have these distinct objects, at least not generally. So what could happen is that rainbow pixel is actually like the discriminator between being object A or being object B. So the level of abstraction may increase, just not in the way you would expect it to be.
I don't know whether you agree with this, Alex, but I love synonymizing abstraction and extrapolation. And they mean slightly different things in different contexts. So if we start with neural networks, we're in the Euclidean domain. And the way that the approximation, because if you think about it, all we're trying to do is say, here's the training data, and we want to generalize around the training data, and we could do it with an epsiloid. We could do it the way decision trees do it. Neural networks, it turns out, they use this beautiful technique of being able to turn on all of these different hyperplanes, which are represented by all of the neurons in the neural network. And there are combinatorially many of them. An input example comes in, the hyperplanes get turned on if they're on the right side of the ReLU boundary, and it creates all of these little honeycomb structures. And those honeycomb structures are how we generalize outside of the training range. But I want to take it a step further. So when we talk about extrapolation, what that really should mean is being able to use a pattern in different parts of the input space, just like a CNN does. So a CNN would recognize a tennis ball in any part of the input space. And that's because the prior does this translational weight sharing. So it kind of shines the pattern over the input space. And then we have system 2 extrapolation, which I would say happens, it's the same thing, but happens in more of a logical domain, where I can use some information that I've learned and I can extrapolate broadly into many new situations in experience space. So that doesn't seem very geometric anymore, does it?
No, but what exactly do you mean when you say you talk about like certain objects in that space? What does it actually mean that you do logical inference about something, for example? Because I can tie like a logical inference procedure to pretty much anything arbitrary. That may not mean that the actual reasoning may be sound in the real world, but that's also nothing that's guaranteed. Maybe the difference between like a human and like a neural network is just the way a human guarantees that certain things correspond to the real world. So basically, that the human guarantees certain semantics. And because they guarantee certain semantics, they can start reusing parts. Just because he knows like, if X, then Y, then you can reason that if you actually see X, then you can give me the Y. And these are the general rules you can apply anywhere. However, even if a neural network might learn that, there's no reason that this X implies Y relation is actually something that has any correspondence to the real world.
That's really interesting. I think semantics are really important for extrapolation. And one thing I'd like to explore in a minute is that in neural networks, because if we think of semantics as being the mapping between things, and in neural networks, there are still semantics because there are still mappings. A neural network is a bunch of mappings, but all of the mappings are on the same level. They all just mean a kind of similarity in the most basic sense. So it's very difficult to reason over that because they're all on the same playing field. But just before we get there, I think one of the mental blocks I have is, in light of the spline theory, I think of neural networks as being locality-sensitive hashing tables. And the kind of logical inferences that you're talking about requires a function, or it requires some kind of computation. So extracting a particular polytope from the ambient space and then summing up all of the distances from the faces of that polyhedron, that seems to me completely different to executing a function.
Yeah, it is. So I think that is one of the major differences between something like a symbolic regression and like neural networks. That the way they handle things, like neural networks are inherently continuous just because of the way they model things. And continuous things don't really handle well when you take them somewhere different. Just because there's so many degrees of freedom in a continuous space that there's very little to actually work with in like generalizable rules. This is why we always use linear layers, because linear layers are something that is pretty easy to say, well, if something is true in some range, and if you just permute it a little bit, it's probably still going to be true. Discrete objects don't really have that property because, well, there is no notion of permuting a discrete object by a small little bit. Because once you are in that abstraction range where you have discrete things, like permuting by a small bit doesn't have any meaning anymore. You can either permute it by just completely changing it, in which case, well, then the inference procedure obviously also changes, or you can do nothing, because you can't just go by an epsilon into the entire range.
So this distinction, that we're making between continuous structures versus discrete structures, it also comes up in the exact same context of talking about the difference between iterative compute in a complexity sense versus just a circuit, whether it's forward pass, just some finite kind of circuit that does a thing. And the frequent response is, well, yeah, but we have the universal approximation theorem, well, if we have an infinite neural network, it's Turing complete, all these kinds of things. I think that completely misses sort of the point that in any practical scenario, in any practical number of neurons, in any practical number of time steps, these different computations are capable of doing very different things. So I wonder if, how would you respond to a connectionist, for example, who comes around and trots out, universal function approximation theorem or something for evidence that there's no difference between discrete computation and continuous.
I think that's a big disservice to think about what could happen in the limit. Because in the limit, for example, the limit of infinite time, everything is decidable. In fact, it's a big difference about what's happening in even a very, very large finite case versus what happens in an infinite case. For example, there was a recent paper called Why Would I Trust You, Bellman, which basically looks at these Bellman iterations in reinforcement learning. And what they do is they basically see that kind of you can decrease the Bellman error while still having equally good policy, because basically we can shove everything into the infinite. I believe that even if something as in the absolute limit, like in the absolute infinite case, is actually equal, that is really that's really not a useful statement. There's also a different issue with the universal approximation theorem, because in most cases what you try to do is you have a function and you try to basically approximate that function. That's why it's called that way. But in practice, you don't actually have a function in machine learning. You have samples from a function. And
good point.
And that changes things entirely, because suddenly you only have finite support. And even if I blow it up to infinity, if there's a space between two samples, which you would, in the ideal case, want to sample, you can't because you don't have any samples there. So this is another where infinity is kind of hidden, because you have this infinite amount of values you could potentially sample, even though in any practical scenario, there's only a very, very finite amount.
So before we leave behind, discrete versus continuous, this almost perennial theme on machine learning street talk, I just want to ask you to wax philosophical for a moment about the universe, because, it's an open question as to, if you go fine enough, down to the Planck scale or below, who knows, is the universe some type of a discretized, computational mesh, whether it's a hypergraph or a grid or some asymmetric lattice, who knows, or is it at the deepest imaginable layer still continue to be, continuous forever? What would you guess?
Well, if we use my minimal knowledge of physics, there's always kind of this duality between having continuous things like waveforms and having discrete objects. So I believe if you actually go down to the absolute lowest level, it probably doesn't matter. What does matter, however, is that in practice, what you would want is to have some decision has to be made. Because at some point you're going to have to decide, do I push the button? Do I escape out because I see some other car coming in front of me? Or do I not? And starting there, you are going to have discrete decisions, because you're going to have to push the button or not push the button.
Well, not necessarily, because there's decisions like, should I apply 1.2 newtons to the gas pedal or 1.203 newtons to the gas pedal? So there are problems that are still, continuous in nature. I mean, we need to still give out continuous answers, right?
Yes, but there's always the fundamental question of, do I even give an answer? Do I change what I'm doing, for example? So
okay, so you're saying you can't escape the discrete decision. You can't escape some discrete decision, even if you have coexisting continuous, quantities.
Yeah. At some point, there are things that are just irreversible. There are things where you go over a hill and you can't go back. And once you have that, you have a discrete thing.
Right.
Alex, I know that you're really interested in search, and I think we can tie a few threads together nicely here. We're speaking with Stanley later today, and he has this concept of interestingness. And actually, I love this conception of just thinking about our lives as being a kind of search problem. I'm really interested in this notion that greatness could just be a door in a maze, and it's within walking distance, and we could just go and open that door and find it. But unfortunately, there's combinatorially many doors, and we need a kind of serendipity or subjectiveness to find it. Stanley calls it interestingness. Clearly, a completely random search would be a dumb thing to do.
I'm of two minds actually about this. So on the first hand, I very much like the idea of having very good heuristics. For example, for things like, in my case, for example, theorem proving, where it's the case that there are billions of different things to try, but you want to kind of narrow it down to the interesting parts. And then you want to have these clever algorithms, which, for example, they learn from failures. They know because this and that didn't work, I can infer that about the solution. So you want to have these interesting things, but also you don't want to waste your time searching into a completely wrong direction. On the other hand, I'm always careful now, like as of recent specifically, with phrasing everything as a search. Because a search kind of entails you have a goal. I'm not sure if that's true in every circumstance nowadays, or at least in machine learning. Because what would be the goal of having like a perfect classifier for cats versus dogs, for example? Well, you could just say, well, it's perfect on the training set, but that's not what you want because then it's overfit. You want to say it's perfect in the validation set, but that's also not enough. What you want to say is, given infinite data, I want it to be perfect. So kind of and you just implicitly define that by saying, well, I can't give you the infinity, I can give you a small chunk of it. And the problem now is, the problem is basically underspecified. Like the search goal, there are many, many different goals, and even if there is a door you find, it may not be the unique door you find. There may be hundreds of thousands of doors, which from your point of view of the implicit definition are all equally good.
I must admit, it sounds counterintuitive because Kenneth Stanley says that the best way to find what you're looking for is to not look for it. And the stepping stones in those mazes, they could be goals, they could be objectives. And he says that the best way to have a system like this is to have no objective at all, or to have an infinitude of objectives. So in some sense, you're finding stepping stones. So you're discovering objectives that you don't know about. And then it gets very murky. So it's almost like he's saying, whatever you think you want, actually, if you explore down that part of the corridor in the maze, you'll discover something even better, and then you'll start optimizing on that. I posed a question to someone yesterday. Imagine you wanted to be a billionaire. How would you come up with metrics to optimize that monotonically? And it's a very difficult question. The only metric that you can come up with, it's similar to the concept of densification and reinforcement learning. You can design metrics in such a way that they seem to be a little bit more impervious to deception. So, for example, you could use the concept of diversity as a metric, or Stanley uses the concept of information accumulation or behavioral entropy as a metric. So these are things that seem like you can monotonically optimize them, and they're still interesting enough so as to not be a completely random search.
There's a field called inductive logic programming, which is basically the idea that you induce a logic program by maybe just doing like a random search, or usually it's something very clever, basically a slice up the hypothesis space. And the important part about this is that you don't actually want to have a solution, because a solution is just going to be basically one predicate for every piece of the training examples, which just says this is, for example, you have 1,000 cats and it's just a predicate says cat number 1 is a cat number 2 is a cat, and so on. What you want to do is you want to have the most general solution. So, and then you already start running into problems. So the first problem is, how do you define whether or not two things are more general than another? And if you try to do that, you very quickly get to the idea, well, I actually have to prove that you can derive the more specific one from the more general one. And people very quickly notice that this is impossible, because you get it into decision problems instantly. So what they nowadays do is they do something called subsumption, where basically they approximate this idea. But let's say you actually have an oracle, which can actually perfectly tell you which one is more general. So it actually can solve this decision problem for you. Then you still have the problem that two things can be more general in two very different ways. So let's say you want to sort a list. Is merge sort more general than a heap sort? I don't know. There's no notion of being able, there is no unique order, there's no unique total order which gives everything which sorts everything. And this is the same problem in many search problems, because suddenly you have to, even if you do completely like random search between random objectives, you still have to figure out, did I actually achieve what I wanted? Like, did I find what I want, or is maybe that other part is still more close to the objective?
So I think my take on this, and you guys are going to have to bear with me for a little bit because it's going to get slightly philosophical, but I think there are these dualities between a parallel set of concepts, and those concepts are past and future, knowledge and control, exploration and exploitation. And I've been thinking about this for decades, ever since I saw this beautiful quote by Claude Shannon, the information theory guy, right? He said, "We may have knowledge of the past, but we cannot control it. We may control the future, but we have no knowledge of it." And what that made me realize as well is that the same duality exists between science and engineering. So if you think about, what does a scientist do? A scientist leverages control to gain knowledge. They set up controlled experiments to gain new knowledge. An engineer does the inverse. They leverage knowledge to gain control over the future. And the same with this duality of the exploration versus exploitation trade-off. So I think part of the reason why a lot of the times we're talking past each other or going around in these circles is we've got these two different, really dual, domains, and you have to kind of operate in both at the same time. And so Stanley has a great point about, look, if we're just dumping all our resources really into engineering problems, getting better control over the future, building a rocket that goes slightly faster or, uses a little less fuel, or even if we're doing similar types of things in science where we're just refining the knowledge base that we already have, right, and just making it more and more precise, we're not doing the exploration phase of things. And so we're never likely to really greatly expand that sphere of knowledge. So I think, this is the problem, is that we have this duality, we have these cross purposes, and there really is this weird asymmetry. I mean, it's starkly apparent with time. It's this really bizarre thing. Like, time is this bizarre concept that befuddles, anybody who tries to think about it, because we have this very sharp cutoff. I can't change anything about the past, and I can't know anything about the future. Maybe we're just trying to meld two dual spaces that need to remain complementary, forever.
You have to manage what you know, but also try to expand what you don't know. However, I don't think they are quite that they are quite mutually exclusive. That you can do one, but then you have to not do the other. Many of the big engineering advancements sooner or later are going to lead to theoretical advances, and the other way around. The theoretical advances lead to big engineering advances.
I don't deny that there's a connection there, for sure. I think they're like this dynamo. They keep rotating and feeding back to one another, but I think they're very different tasks. I mean, if we think about the most distilled context of this, say the multi-arm bandit, right? I mean, there you're at the situation that you gave earlier where you have a discrete choice. Which arm am I going to pull? I can pull one that will teach me something new and maybe give me a reward, or I can pull one that I'm just sure will give me a reward. But this dichotomy there exists. I mean, there is, an arm may be giving you both. Like, an arm may be giving you both knowledge and reward, but you're analyzing them as really separate, spheres. Like, I have my uncertainty quantity and I have my reward quantity. So even though they are connected and they feed back to one another, they do require almost this separate sphere of analysis, even if it's linked.
I'm reminded of, I think it was the book of Feynman, so Feynman's book, where he talked about kind of the idea that scientists, generally speaking, have a multitude of solutions and no problems to solve, and engineers, generally speaking, have a multitude of problems and no solutions to them. And what
Right.
And what he basically advised people in that book is to say, just like if you're a scientist, you know you're going to have like solutions anyways. But what it advises is have a couple of problems, like maybe 5 or 6 or maybe as much as 10, just have them in the back of your mind. And every time you find a new solution that may be like completely devoid of any meaning in of itself, just take that solution and try to plug it into one of your problems, or basically all of your problems, and try to figure out, like, can I get like a new step? And that's an interesting idea. It's stuck with me.
Well, it could be worse. You could be a mathematician who has both tons of problems and solutions that have no connection to the real world for now, and you're waiting for the day in which somebody finds a connection that is useful. All right, you're quite broad. You have a broad knowledge base, right? And I'm wondering, so number one is maybe the work you're doing is so difficult and ambiguous, and the problems you're trying to solve are so general that it requires like a very large, knowledge base, or it's just that you're very broadly interested, and you may be a jack of all trades, if you will. I'm just kind of curious about how you got to where you are now with that breadth of knowledge.
Mostly interest. So, I never was really that interested in going like optimizing the last like couple of percent. Like I know I have some friends which like you can have a program and they can optimize it to the wazoo. Like they sit at the same problem and just do that very, very like to an awesome level. Like, I don't know, at our Discord, for example, with Lucas, which does these large language models and basically then knows like the specifics of like how TPUs internally work and the communications between them. Like, I could not motivate myself to like actually learn that. But what I can do is I can look at certain difficult problems and learn about those. That it isn't about actually achieving like a specific goal, but it's more about getting context to whatever I'm doing. And I think that's a good way of learning things. To have that to not be as goal oriented, but rather be as oriented to get much more context to the things you already know. And if you have that context, then you can get context to that context. And that be the goal.
So you're doing
spoken like Stanley.
You're doing a search for interestingness, right? Like the goal is to expand the context. That's interesting.
Yeah, but I've been more and more like getting to grips with that. I cannot do everything. Like, there's some things I cannot research like into any depth, but I think it's important to have broad knowledge about lots of different things. Just because you don't know what's going to be used. I'm talking from a research point of view here, but you don't know what's going to be useful. If you knew it, then it wouldn't be research anymore.
I'm interested in knowledge transfer efficiency. I'm building a code review platform at work, by the way. And, one cynical view is that the transfer of knowledge or even acquiring knowledge is a bit like the curse of dimensionality, a kind of, like information sharing between teams goes up with some factorial relation in respect of the number of people in teams, and maybe even acquiring new knowledge, it just blows up exponentially. But I've had a slightly opposite reaction in some sense. So the more concepts I know, those concepts seem to extrapolate into many other domains. Like anyone who learns about probability theory, for example, will start to see the world in statistical distributions. And it's almost like Tetris, where you have a few things come together, and then the whole problem space just kind of collapses down several layers. So
that's a good analogy.
Yeah. Do you have a similar experience? Because I'm very impressed with how you operate, and clearly you're extrapolating a lot of knowledge from many other domains.
Definitely, I think that knowledge composes very well. It's the idea of that most things aren't actually that different. Like most things that are studied by humans is kind of the same. It's different views on very, very similar problems. I did like a couple of semesters ago, I did a lecture in artificial intelligence, what it was called, where like one of the big ideas was always you can either optimize a problem directly, or you can say, well, let's just relax that problem and just remove some of the constraints, optimize that super easy problem, and then basically go back and just one by one add the constraints. This semester, I took a course called Linear and Combinatorial Optimization, which is about linear and combinatorial optimization. And there also the same idea persists. We have the primal problem, which basically is you have like an initial step, in, for example, the simplex algorithm, and you move up and find a better solution. Or you have the idea of you can start from the outside, from like a dual problem, and move back in. And basically that's adding constraints like one after another. And I think that, for example, this is one of those ideas with two completely different things. Like the one was like automated planning and theorem proving, and the other one was like optimizing across like some geometrical object, basically. And it's basically the same idea. And I think that's true for most things. Like if you look up certain topics, like it's always going to bleed over in something else. Like topology has some applications to category theory, and the other way around, there's tons of things.
I think what you're describing is there are abstract analogies, right, which allow you to extrapolate between domains. But do you think that those analogies are your creation, or are you just discovering them?
So first of all, I don't say that anything of this is my creation. Like that's been known for a long time. But
but I mean, your mental framework to understand the world, is it Alex's framework, or do you think you've just discovered some Platonic framework?
No, it's definitely, it's my framework. It's a human framework of looking at problems. There's a reason that there are some problems in the human in space which are unsolved for like hundreds and hundreds of years, and there are other problems which are probably equally difficult on like an objective level. Whether or not this exists, another question, but which are solved like pretty quickly. I believe the reason is that humans have an inherent like bias towards certain kinds of problems. It's very hard for humans to suss out what actually these biases are. And this is also something where machine learning now has a problem. So for example, in like causality is something that in probability theory, nobody really took a look at, because obviously if the barometer goes up, it doesn't mean that the barometer caused the world to heat up, but the heat caused the barometer to go up. But if for a machine, it's not necessarily that simple. It could be that actually barometer going up affected the world. And I believe that many of those like counterintuitive things are things that are these very, very tough nuts to crack. Like in like causality, in finance, in also mathematics, there are things that just defy like these common mental frameworks, and these are just these impossible puzzles.
There's a lot of discussion at the moment about causal representation learning from observational data. Not just learning the causal factors, but learning the causal structure. And this seems to me to be very related to all the discussion we've just had. So it's related to finding these abstract cognitive categories. If you think about it, the causal structure is a type of cognitive category. And I also think it's related to the concept of geometric deep learning and also to extrapolation, because causality structure is all about being able to extrapolate into different situations and being kind of invariant to all of the things that it shouldn't be connected to. And then the situation gets more complicated because in the real world, unfortunately, everything is correlated. And as we said earlier, unfortunately, in neural networks, everything is linked. Even the blue pixel is probably linked to whether or not we take a certain action. So do you think, I mean, just coming back to causality, in geometric deep learning, we've hand-baked these inductive priors and they work very well. Do you think we could do the same thing for causal structure, or do you think it's actually empirically learnable from observational data?
If you just have observational data, then you can actually show that there are circumstances in which you actually can't learn that. That's one of the core ideas of for example, the dual calculus of Pearl, that there's some things you have to interact with the world to kind of force a decision about certain connections. But I think from if you have that, if you have this interaction, then probably yes. On the other hand, there's always the question, so you can probably learn that, I mean. On the other hand, there's always the question of, does it make sense to actually do this? So even if it's technically possible, is it practically useful? And practically, I would say, I'd be careful with saying that, because finding those causal observations they may involve doing things that are just not practically possible. And you just have to like opine from above and say these connections have to exist. Like for example, there are some things in the medical sphere. For example, dieting is one of the examples where you ask a question of what happens if somebody just eats fish for all their lives. And in practice, you can't actually do that. Like you can't take a meaningful population and say, okay, the entirety of Sweden now just eats fish. So you just have to have some connections which just say, bake that into the architecture. And I believe that and the idea of having priors, so which is kind of the same idea, having an easy framework where you can just say, I know this about the real world. I know the temperature affects the barometer and not the other way around. Being able to have that knowledge and very quickly plugging that into some learning system is going to be like the actual next big thing. We have all the knowledge we already have, like books and books and books. You can just dump into a network and use that as a bias to accelerate everything else.
I think it is important to point out that even the concept of defining causality isn't necessarily straightforward. I mean, there are quite a bit of philosophical, discussions around it, varying definitions of it, counterfactual versus structural, et cetera. So I mean, and it even crops up, at least let's say, choices of convention and how you define causality can kind of have far-reaching effects on what you decide, the meaning of an experiment is. For example, I mean, with even like say in quantum mechanics where people are always talking about Bell inequalities, well, that has the assumption of statistical independence, and depending on which kind of definition of causality you choose, it either is or is not the worst, possible catastrophe if you relax that requirement of statistical independence, right? So it is just worth pointing out for those that want to go and look into this field. There's a lot of variety in how to define this, but I wanted to ask you, Alex, of those various operational definitions of causality, which one do you find is the most practically useful for, let's say, work in the machine learning field?
It's probably Pearl's do calculus, just because it has a very, very probabilistic view with like very minimal axioms you would actually have to introduce. Like you have this do, which basically forces a certain connection, and then basically you run through and basically this calculus and basically does this combinations. It's also very easy to write it down as a graph.
In a lot of sense, correlation is good enough. For a lot of the work that a scientist is going to do, or a machine learning, practitioner, if they can find very strong correlations, then it just becomes a matter of which of these correlated variables can I control or not control, then it almost becomes obvious.
A lot of people criticize machine learning practitioners because of the lack of causality in our models, but this is another thing I see at work actually, which is the lack of counterfactual reasoning is a huge problem with many of the metrics that are used. I mean, Zillow, for example, they recently went out, I think they went bust. And that was because they thought their machine learning models were working very well, but they clearly didn't have a baseline or a counterfactual. The entire market was just going up, and then when it stopped going up, their models broke. I just wanted to finish by talking about discrete program synthesis. So I'm really excited about this. As I said, I'm building a code review platform at the moment, and I think I've got an exciting use case for it, which is when a pull request comes in, we need to inductively categorize a situation. So wouldn't it be cool if we could select some text? We've automatically parsed a bunch of representational information. It might be an abstract syntax tree. It might be a reference graph or something like that. And, we could just select some text and do some back testing and do some inductive program synthesis. What could possibly go wrong? And there are some really cool models out there like DreamCoder, for example, which, supposedly reduce this factorial search space in respect of the program length to a linear search problem, because you now have a neural network which will predict how good some of these sub-modules are in respect of a given task. So does this sound a little bit like snake oil to you, or do you think there's something interesting there?
People are very quick to declare a victory in this space.
Like quantum computing.
There are many, many different things you could do in programming, or like in general. And in specifically in this discrete space, where as soon as you have basically like general lambda calculus, if you can do that, then you can basically Bellstriero can do anything you want. And that leads to big problems down the line. If a model works very well in what you've tested it in, it doesn't mean it goes anywhere else. And you see that in, for example, in theorem proving. There's this idea. So at the University of Matt, at FAU, there is Michael Kohlhase, and he basically, very early, 20 years ago, he said that the current way of building like these reasoning systems is is suboptimal. Because what's happening is people have a great idea, like researchers have a great idea. They build that model and actually it works very well on like some unknown problem. And then they build up that system and at some point like the next system is going to come up and supersede that. What people then forget is that by introducing that new project, it doesn't mean that everything old still works. So, for example, in type theory, there's this hype topic called homotopy type theory, where basically you model everything as a topology. And this works incredibly well for anything like differential geometry, like writing down these kinds of things. But there are some things which just get very, very hard because, for example, you don't have unique identity anymore. So what he came up with is the idea of, well, let's just have a meta system where basically we write down everything else. So basically we have an endpoint for this, an endpoint for that, and the actual system just does translation work between these different calculi. But they've been working on that for like 20 years now. They are nowhere close to being done. And it's always a problem that if you want to do that, you have to go to like levels of generality I cannot even comprehend. This is kind of the problem, because this space is really what would be interesting for machine learning. But even this space basically just says, well, we have that, like these nice rule systems that work very well for specific systems, but we still need one for each of them. And we need an entirely different level to kind of translate between those and again. And basically this meta level always changes because there's some new idea and suddenly like some old assumption doesn't work anymore. Because it's always like this moving goalpost. And this is why I'm very careful. Like there was this OpenAI thing, for example, where they showed like these math Olympiad programs. And for example, they did that in Lean. And I'm pretty sure if you took the exact same system and you trained it on like something like Coq, it wouldn't work as well anymore. Because Lean is very, very good at handling kind of these numerical, like these analysis problems. And Coq doesn't do that as well. It does like the type theoretical, like where you have like completely new type theoretical building blocks. That works way better. But suddenly you lose all these biases you introduce that make the like analysis part very easy. Because suddenly you have things that just never happen in analysis now are possible to happen there. You have to basically guard against them. And you just get that explosion of options.
So what's the moral of the story for Tim in building his business model? Like,
should I just give up now?
Finding the right. No.
Give up now.
It sounds like maybe it's like you need to be careful about which program synthesis paradigm you choose, maybe, that captures the, the important attributes that you're trying to with the program recommendations. Maybe, I don't know. I mean, is that the lesson, Alex?
You have to be careful with the battles you choose to fight. Like there are some things you can do. So, for example, a very popular thing is making sure that this program doesn't have any memory leaks or doesn't have any race conditions. And that's very much doable. There are also entire frameworks like separation logic, which are very well at doing specific things. But they also have some downside. For example, separation logic basically forces you to, if you have some novel like predicate you want to check, you have to define that predicate. And suddenly you have that additional layer of, you have the programmer, which then defines what's supposed to happen. And it's sometimes harder than actually writing a program yourself. And so, but there's some parts of that which you can use and which you can deploy. There's, for example, the Facebook tool called Infer, which, for example, does like memory, safety, and I think race conditions they also do, and some other things. And that's a battle that you can fight and that you can actually win. It's a solvable problem. But if you say, I want to have like arbitrary things happen, or like the closer you go to arbitrary, the harder it becomes. And I believe that ultimately it's going to be like an asymptotic problem where you're never going to get, of course, like provably, you're never going to get to perfect program induction. But you can get very, very close, but it's going to be incredibly more expensive.
Yeah, I have a similar intuition to you. I mean, I think the gold standard, and I'm familiar with Infer, by the way, we use that already. I think the gold standard would be some kind of program recompilation and understanding, and we would actually know what they were trying to do. And I think on the low-hanging fruit side of things, you can think of it as a glorified regular expression where there's some kind of pattern matching using some additional topological and structural information about the code. This has been absolutely amazing. Thank you so much for joining us today. It's been a wonderful conversation.
Yeah.
Thank you, Alex.
Thank you guys too.
It's been great talking to you.
Awesome.
Yeah, always a pleasure.
If you enjoyed the show today, don't forget to like and subscribe and rate us on Apple Podcasts. See you next time.